So friends, welcome back to our YouTube channel. In today's video, we will talk about some subgroup theorems. In the previous video, we have seen the definition of subgroup, and we know that any non-empty subset H of a group G is subgroup of G if and only if H is closed for composition defined in G, that is if A and B are elements of H, then AB must be element of H, and H itself must be a group for the composition induced by that of G. Okay, so now we will start theorems. So first theorem is if H is a subgroup of G, then identity element is same in H and G. Inverse of any element A in H is same as inverse of same element A in G. Order of element A in H is same as order of A in G. So basically what are they telling us? They are telling us that if H is a subgroup of G, then identity element will be same, it will be unique. Also inverse of any element will be unique in H and G. Also order will be same in H and G for any element, right? So let's see the proof. So here we have considered that to show identity element is unique in H and G, first part's proof. Let's consider E be the identity element of G and E dash be the identity element of H. So here we have considered E and E dash as identity elements, and we are considering that there are two different types of identity elements, E and E dash, for the same element in H and G, and then later we will show that E and E dash are same, so there is unique identity element. So if A is element of H, then we have considered that E dash is identity element of H. So A into E dash is equal to E dash into A is equal to A. Also H is subgroup of G, hence as A is element of H, it is also element of G. Then A into E is equal to E into A is equal to A, since E is identity element of G. And from these two equations, we can say that A into E dash is equal to A into E. We have taken these two left hand sides just, and we know that cancellation law holds in subgroups also. So by cancellation law, we cancel out this A from both sides, so we get E dash is equal to E, and this shows that E dash and E are not different but they are same, hence identity element of H and G is same and it is unique, right? So now let's go to the proof for second part. So our second part was that if inverse of any element A in H is same as inverse of A in G. So if we took any element, then its inverse is same in H as well as G, that is in a group as well as subgroup. So let A is element of H, and as H is subgroup of G, hence A is also element of G, right? Suppose B and C are inverses of A in G and H respectively, and E is the identity element of G and H, and we have just seen that identity element is same for G as well as H. So AB is equal to BA is equal to E, because B is inverse of A in G, and we know that A into A inverse is identity. So AB is equal to BA is equal to identity. Also C is inverse of A in H, so AC is equal to CA is equal to E. And from both these equations, we can say that AB is equal to AC. We have taken just this part, left hand side. And also then by cancellation law, here we cancel out AA and we say that B is equal to C, right? Hence B is equal to C. B and C are same, and hence inverse of any element A in H is same as inverse of A in G, and hence this is the proof for second part. Now let's go for the third part. In third part, we have said that order of element A in H is same as order of A in G. In short, order of any element is same in group as well as subgroup. So let's see how is it. So we consider order of A is H, order of A in H is M, and order of A in G is N. We are considering two different orders of same element in group and subgroup, and later we will prove that these two different orders are not different but they are equal, that is we will show that M is equal to N. So let E is the identity element of G and H, as we have just seen that identity element is same for both groups and subgroup. So as M is order of A, so A raised to M must be identity, and this is by definition of order of element, right? And also N is order of A in G, so A raised to N is also identity, since M and N are order of A, right? And here also we can take them as equal because their right hand side is equal, so left hand side should be equal. So A raised to M is equal to A raised to N, and now we will multiply both sides by A raised to minus N. So A raised to M into A raised to minus N is equal to A raised to N into A raised to minus N. A raised to N into A raised to minus N will give A raised to 0, that is nothing but identity, right? Also, A raised to M into A raised to minus 1 minus N will give us A raised to M minus N, we can say. And by comparing their indices, we can write M minus N is equal to 0 by indices rule. So, M minus N is equal to 0 implies that M is equal to N. And so, orders M and N are not different but they are same. And this shows that order of A in H is just same as order of A in G. So this was the complete proof of first part, and from these three results we can say that if H is a subset of G, then H will be subgroup of G if and only if it follows the following properties. If A is element of H, B is element of H, then composition of these elements AB is element of H. That is, if we took any two elements of a given subgroup, or we can say given subset of a group, then composition of those two elements means whatever operation is in the group, under that operation these both elements composition must be again the element of that set of the group. Then second property is, if E is identity element of H, then E is identity element of G also, that is the identity element is same, that is unique. Also, if A is element of H and A inverse is element of H, then A inverse should be inverse of A in G also. That is, inverse for any element A is same in H as well as G, right? So this is all about the first theorem. Now let's go to the second theorem. If H is a non-empty subset of G, then H is a subgroup of G if and only if A is element of H, B is element of H. This implies that AB inverse is element of H. So we have given here that H will be subgroup of G if the given condition will be satisfied, and the given condition is that A and B are elements of H, and it implies that AB are elements of H implies that AB inverse is also element of H. So let's see the proof. We consider H as a subgroup of G and AB are elements of H. As B is element of H, B inverse is also element of H. Also we can say that if A is element of H, then A inverse should be element of H, right? So now A is element of H, B inverse is element of H. Hence AB inverse is also element of H. This is by closure property of subgroups. We have proved the first proof, that is straight proof, and we have to prove now converse. We have considered this as subgroup and we have proved that the condition is true. Now we will consider that the condition is true and we will show that the H is subgroup of G. So let's go to the converse. So suppose the condition is true in H, then we have to show that H will be a subgroup, right? Then from given condition, we can say that H is non-empty as A, B and B inverse are elements of H. So what was the given condition? Given condition was that AB are elements of H. Then AB inverse must be element of H, right? So we can say that we can see that H is non-empty because A, B and AB inverse are elements of H. Also, as it is non-empty, then identity element will exist there. So existence of identity elements and non-empty is done here. Again, identity is in H. We have just said that identity exists. Also, B inverse is element of H. Also, A inverse is element of H. Then E into A inverse is equal to A inverse, which is element of H again. So inverse of every element exists in H, right? Again, A is element of H. B inverse is element of H. Then by given condition, what is given condition? We are given two elements. of H, then AB inverse will be element of H. And here we are saying that A is element of H, B inverse is element of H. So we can say that A into B inverse is also element of H. But A into B inverse is nothing but A into B. So A into B is element of H, and hence H is closed. As all three properties of a set to be a subgroup are satisfied, it is non-empty, that is identity element is exist, closure property is satisfied, also inverse exists for every element, and hence we can say that H is a subgroup, right? So in this video we talk about some subgroups theorems. We have seen two subgroups theorem, that is if H is a subgroup of G, then identity element is same in H and G, also inverse is same in H and G, also order of element is same in H and G. And in the next theorem we see that if H is a subgroup, then A and B are elements of G, implies that B inverse is element of G, and we see this vice versa. In the next video we will talk about some more theorems related to subgroups. So please do like, share and watch our videos. Thank you.